Right now, something impossible is happening beneath the Atlantic Ocean. A volcano is building land where no land should exist. Steam and ash tower 15 kilometers into flight corridors used by thousands daily. What force can reshape an ocean in real time? What happens when Earth's crust tears open in waters shallow enough to touch the sky? And why are scientists calling this the geological event of the century? Off the coast of Portugal, 650 kilometers west of Lisbon, the ocean is boiling. The water churns white and violent across a zone 300 meters wide. Beneath the surface, magma at 1200 degrees Celsius collides with seawater in explosions that shake the seafloor every 18 seconds. This is not Surtsey. This is not Iceland. The eruption site sits directly on the Mid-Atlantic Ridge, the underwater mountain chain that splits the Atlantic floor from the Arctic to Antarctica. Here, the Eurasian and North American plates pull apart at 2.5 centimeters per year. That spreading has continued for 200 million years, slowly widening the ocean, creating new crust in silence and darkness. But what makes this event unprecedented is depth, or rather, the lack of it. Most Mid-Atlantic Ridge volcanism occurs at 2,800 meters below the surface. At that depth, crushing pressure suppresses explosions. Lava oozes quietly onto the seafloor, forming pillow basalts that cool in seconds, never reaching the sky. Here, the vent sits at just 198 meters depth, shallow enough for sunlight to penetrate, shallow enough for phreatomagmatic fury to punch through the ocean's skin. The first tremors registered on December 24, 2025. Hydrophones deployed by NOAA's Pacific Marine Environmental Laboratory detected low-frequency harmonic tremor at 1.8 to 3.2 Hz. The signal was continuous, rising and falling like breath. Within hours, the Portuguese Institute for Sea and Atmosphere logged micro-earthquake clusters at magnitudes between 1.4 and 2.8, all originating from a single point on the ridge. This was not normal background seismicity. The tremor signature indicated rapid magma ascent through fractured crust. By December 25th, seismometers on the Azores recorded over 400 events in 12 hours. The swarm migrated vertically, tracking magma as it rose through the final kilometers of rock. Temperature sensors on nearby oceanographic moorings spiked from 4 degrees Celsius to 68 degrees within 90 minutes. The ocean was about to break open. On December 26th at 0417 UTC, satellites captured the moment. A circular disturbance appeared on the surface, expanding outward in concentric rings. Steam geysers shot 40 meters into the air. Thermal imaging revealed surface temperatures exceeding 90 degrees Celsius across a zone the size of 3 football fields. By 0600 UTC, the eruption had breached the surface entirely. Research vessels stationed 12 kilometers away reported thunderous detonations every 15 to 20 seconds. Black ash mixed with steam, forming a roiling column that climbed to 8,000 meters before wind sheared it eastward. International volcanology teams scrambled to position monitoring equipment. What they were witnessing had no modern parallel. When magma meets seawater at shallow depth, the interaction is catastrophic. Seawater at the vent site flashes to steam in microseconds. The volume expansion is explosive, shattering newly formed lava into microscopic glass shards. These fragments become airborne ash. But the water keeps coming. Each explosion pulls more seawater into contact with molten rock, sustaining a feedback loop of steam, pressure, and fragmentation. Temperature measurements from autonomous underwater vehicles revealed magma temperatures between 1150 and 1230 degrees Celsius. The basaltic melt is rich in iron and magnesium, sourced directly from Earth's mantle. Its low silica content makes it fluid, fast-moving, capable of spreading across the seafloor before the next explosion tears it apart. The frequency of phreatomagmatic blasts averaged 1 every 18 seconds during peak activity. Each explosion ejected an estimated 200 to 400 cubic meters of fragmented material. Some particles landed back in the ocean within seconds. Others rode the thermal column into the stratosphere.
What no one predicted was land. By December 28th, sonar mapping revealed a structure rising from the seafloor. The volcanic edifice had grown 180 meters vertically in 48 hours. Its summit now sat just 12 meters below the surface. Lava flows extended outward in 4 directions, building a platform 600 meters long and 320 meters wide. On December 30th at 11:42 UTC, the summit broke the surface. A jagged ridge of black basalt emerged from the steam, glistening and hissing as waves washed over it. By nightfall, the ridge extended 140 meters above sea level at its highest point. The new peninsula was growing at an average rate of 2.4 hectares per day. Lava fountains fed rivers of molten rock that poured down the flanks and solidified at the waterline, extending the land outward like fingers. Thermal cameras showed surface temperatures on the freshly cooled rock ranging from 400 to 700 degrees Celsius. But the growth was not stable. Sections of the eastern flank collapsed repeatedly, sending debris avalanches into the sea and triggering local tsunamis with wave heights up to 1.8 meters. The eruption is doing more than building an island. It is deforming the entire ridge system. Satellite interferometry data from the European Space Agency's Sentinel-1 constellation detected seafloor uplift extending 45 kilometers from the eruption site. The displacement measurements showed vertical movement averaging 8 to 14 centimeters over 12 days. Near the vent, uplift reached 1.2 meters. This is tectonic recharge in real time. As magma drains from deeper reservoirs to feed the surface eruption, pressure drops below. The surrounding crust responds by flexing upward, adjusting to the new mass distribution. Strain gauges on the islands of Terceira and São Miguel, 280 kilometers east, registered nanostrain expansion consistent with ridge parallel extension. The Atlantic basin is widening faster than its long-term average, driven by the immense volume of magma being injected into the rift. Geophysicists estimate the eruption has already released between 0.08 and 0.14 cubic kilometers of magma. For comparison, the 1963 Surtsey eruption in Iceland produced 0.1 cubic kilometers over 4 years. This system is moving faster. Above the surface, the eruption plume poses a different threat. At peak intensity on January 1st, the steam and ash column reached 15,200 meters altitude. That places it squarely in the North Atlantic Flight Corridor, one of the busiest airspaces on Earth. Volcanic ash melts at 1100 degrees Celsius. Jet engine combustion chambers operate at 1400 degrees. When ash particles enter an engine, they melt instantly and re-solidify as glass on turbine blades, choking airflow and causing flameout. The International Civil Aviation Organization elevated the alert level to red on December 29th. Over 320 transatlantic flights were rerouted south of the eruption zone. Airlines reported delays averaging 4 hours as planes burned extra fuel to avoid the ash. Volcanic ash advisory centers tracked the plume using satellite imagery and computer models. Forecast trajectories showed ash drifting northeast toward Ireland and the United Kingdom. Trace concentrations reached Scottish airspace on January 3rd, triggering temporary closures at Edinburgh and Glasgow. The economic cost of rerouting alone exceeded $18 million in the first week. On the ocean's surface, pumice rafts drifted eastward in slicks 12 kilometers long. The porous volcanic rock floats, creating navigation hazards for vessels. Ships reported fields of pumice so dense that propellers became clogged, forcing emergency stops. Submerged volcanic debris posed an even greater danger. Sonar detected rubble mounds extending 800 meters from the main edifice, some rising to within 15 meters of the surface. These obstacles sit directly in shipping lanes used by commercial vessels traveling between Europe and the Americas. Maritime authorities issued nav area warnings covering a 50-kilometer exclusion zone. The International Maritime Organization deployed survey vessels to map the new bathymetry and update nautical charts. But the most urgent concern is not ash or pumice, it is collapse. The new peninsula is unstable by design. Lava piles rapidly on steep submarine slopes without time to consolidate. Sections of the edifice are hollow, riddled with gas pockets and unconsolidated rubble.
If a significant portion collapses into deep water, it will displace millions of cubic meters in seconds. That displacement generates waves. Tsunami models run by NOAA's Center for Tsunami Research simulated worst-case scenarios. A flank collapse involving 0.02 cubic kilometers of material could produce waves 3 to 5 meters high at the Portuguese coast, arriving within 45 minutes. Larger collapses could generate transatlantic tsunamis, affecting the Caribbean and eastern United States. In response, NOAA activated 6 DART buoys in the eastern Atlantic. These deep ocean assessment and reporting of tsunami systems use seafloor pressure sensors to detect passing tsunami waves. Data transmits via satellite to warning centers in real time, providing critical minutes of advance notice. The buoys switch to event mode when pressure anomalies exceed detection thresholds. So far, only minor fluctuations have been recorded, consistent with surf generated by ongoing explosions. But the systems remain on high alert. One collapse is all it takes. International emergency response agencies are coordinating. The Portuguese National Authority for Emergency and Civil Protection activated coastal evacuation protocols for communities within 10 meters of sea level. Similar preparations are underway in Spain, Morocco, and the Azores. To date, no casualties have been reported. The eruption site is remote, far from population centers, but the expanding hazard zone and unpredictable behavior mean the window for response is narrowing. For scientists, the eruption is an unprecedented opportunity. Submarine eruptions are notoriously difficult to study. Most occur in deep water, beyond the reach of real-time observation. By the time researchers arrive, the event is over. Here, the shallow depth allows direct access. Remotely operated vehicles equipped with high-definition cameras have descended to the vent, capturing footage of lava fountaining underwater and interacting with seawater. The imagery reveals processes never seen before: pillows inflating and bursting, gas bubbles spiraling upward, magma feeding directly into fractures that glow orange against the black seafloor. Sonar mapping tracks land growth in real time, measuring how quickly the peninsula extends and how its morphology changes with each new flow. Scientists compare this event to Surtsey in Iceland and Hungatonga Pai in the Pacific, both of which created islands through similar processes. But those eruptions unfolded over months or years. This one is accelerating. Samples collected by submersibles reveal a basaltic composition with 48 to 50% silica, typical of mid-ocean ridge magma. The iron and magnesium content is high, indicating a mantle source at least 60 kilometers deep. Trace element analysis points to partial melting of asthenospheric peridotite, the same process that creates oceanic crust worldwide. The eruption is not an anomaly. It is Earth's normal business, happening where humans can finally watch. The long-term fate of the new peninsula depends on several factors. Will the lava supply continue? Basaltic eruptions along mid-ocean ridges can persist for years or extinguish in weeks. If magma flow ceases, erosion begins immediately. Wave action is relentless. Storm swells in the North Atlantic exceed 8 meters during winter. Uncemented volcanic rock erodes rapidly. Surtsey lost 20% of its initial area within 5 years. For the new land to survive, the eruption must deposit enough material to build a foundation above wave base. Low silica basalt is more resistant to erosion than pumice or ash, but only if it solidifies in thick, massive flows. Cooling times matter. Rock exposed to air cools faster than submerged material, forming a carapace that resists wave attack. The faster the peninsula rises, the better its chances. If it endures, the land will eventually support life. Lichens colonize barren lava within months. Seabirds bring seeds in their droppings. Within a decade, pioneer species could take root. But survival is not guaranteed. This eruption reveals something fundamental about Earth. The planet is not static. Continents drift, oceans widen, mountains rise and fall. What seems permanent is temporary. What seems impossible is routine. The Atlantic Ridge is the longest mountain range on Earth, and most of it has never been mapped. The forces that split Pangaea apart 200 million years ago are still active, still tearing the Atlantic wider, still building new crust. Humans witness fragments of this process: Surtsey in 1963, Capelinos in 1957, Cavachi in the Solomon Islands, which erupts every few years and build islands that vanish within months. These are not anomalies. They are snapshots of planetary metabolism, the constant churning of rock and heat that keeps Earth alive. The new peninsula off Portugal is not just land, it is proof that the map is never finished, that ocean floors rise and continents shift, that what we call solid is fluid on geologic time. Scientists know the eruption is driven by tectonic spreading and mantle upwelling. They know the magma composition and the mechanism of phreatomagmatic explosions. They can measure growth rates and model tsunami risk. What they do not know is when it will stop, or whether the land will last, or if this is the beginning of something larger, a pulse of activity that could reshape the entire ridge system. The data is incomplete, the models are provisional, the outcome is uncertain. And in the Atlantic, the ocean keeps boiling, the land keeps rising, and the map changes with every wave.